Hello everyone, today with us we have Avyaktha Achar from SMU Bangalore. He is a second year over here and today he's going to talk about Zermelo Fraenkel set theory. His interests are in mathematical logic and set theory. Over to Avyaktha.
So, good morning everyone. So the main aim of today's talk will be to introduce the main ideas of Zermelo-Fraenkel set theory, particularly including the axiom of choice. So the main aim will be to convey all the crucial ideas which are used to formalize set theory, like axiom by axiom. I try to motivate all of the axioms, also at least state many of the major theorems, and try to give some hints so that you can think about it and try to formulate a proof vigorously. I want to convey one of the key ideas used to formalize things like infinity and counting, ordinals, cardinals, etc. So that you have a general overview of the subject and can read more about it. Okay, so let's begin. So I'll start by trying to motivate why we need an axiomatic approach to set theory and what happens if we just think of sets intuitively like they used to do back in before the 1880s or 1890s. Before these mathematicians like Cantor and Dedekind came in and axiomatized everything. So the first section will be nice set theory. So this was the kind of set theory which was done before it was axiomatized, and it was played with many paradoxes. So one of the main issues with this version of set theory is this notion of unrestricted comprehension. So this wasn't directly stated, but it was the root cause of many of the issues and paradoxes. And what this basically says in formal language is that for any property P, so what exactly the property is not, it wasn't that well defined back then, but it's some kind of well defined characteristic of some object. There exists a set of which we write like this, set of all x such that it satisfies that property. So this was something that was assumed during the earlier days, and this gave rise to many paradoxes because certain mathematicians like Burton and Russell, they chose some very weird choice of this property, and the first one is called Russell's paradox. I'm pretty sure all of you have heard about it, so I'll just tell it in words. So this paradox came by taking the property P of x to be x does not belong to x. So if this unrestricted comprehension was true, then we would get a set S of all x such that x does not belong to x. Now because this is a set, it's supposed to be well defined. So given any object, we should be able to tell whether that object belongs to this or does not belong to this. So let's look at S itself. So either S belongs to S or S does not belong to S. Can S belong to S? Can someone tell me? What happens if S is over here? Then it must satisfy this condition. So that means it doesn't belong to S, which is a contradiction. So it must be the case that S does not belong to S, but it satisfies the very condition which defines S. So it belongs to S. So both of these give a contradiction. So there is clearly something wrong over here, and we will try to remedy that with the axiomatic approach. I quickly tell you about another paradox called Daly's paradox, which is a semantic or a linguistic paradox, and that paradox is obtained by taking the property P of x. It says that x is a positive integer which can be defined in at most 100 letters. When I say 100 letters, I mean using standard English language and standard words can be defined in less than or equal to 100 letters. So let T be this, the set which we get corresponding to this property is the set of all x such that P of x holds. So it's clear that T is a finite set because there are finitely many alphabets in English language So if the allotted is only 100 letters, you can make finitely many definitions using that. So there exists an integer, let's call it p, which is the smallest positive integer, not in t. So because this p does not belong to this set, that means it cannot be defined in less than 100 letters. But the definition of it is right in front of you. This smallest positive integer not in t. That itself is a definition for this using less than 100 letters. So because it can be defined in less than 100 letters, we conclude that t is in t. But by definition, it is not in t. So there is again something wrong going here. So many such paradoxes were discovered back in the days, and so we need to find some way to resolve such issues, and that's why we need an axiomatic approach. And you will soon see that the way in which we are going to fix this issue is by an axiom called the axiom scheme of specification, which basically allows you to apply a property only when you already have a set. So you cannot talk about all sets satisfying a property. You need to have some set like K or something, and then you can specify those members which are already in K with satisfy properties. So you need an extra condition like it belongs to K such that X does not belong to X. Those kind of stuff will avoid these paradoxes. And the way this paradox is fixed is by being more particular about what kind of things you can use as properties. So this is something which is not a valid property or which is called formula, because you cannot write it using logical symbols like and, or, not, there exists, etc. So that's how we are going to resolve such issues.
How is t?
Because this is the definition of t using less than 100 letters. Okay. The smallest integer not in t is the definition of t in less than 100 letters. So because it satisfies this property, it's in t. But by definition, it's not in t. So that's an issue. So before moving into the axioms of ZSC, so this Zermelo Fraenkel set theory is axiom of choice. In short, it is called as ZSC, and it is a very popular approach to set theory using axioms. There are other approaches like Von Neumann, Bernoulli set theory, etc. But today we'll be focusing on this one. So before we look at the axioms, let's just see an informal view of how we want our sets to look like once we actually axiomatize them. So there's going to be a hierarchy of sets. And so there's some notion called atoms, or some call it as U elements also, if I get the spelling right. So these are basically, they are members of sets. These atoms are what we want to be members of sets, but they themselves are not sets. So when we're studying, we might encounter something which cannot be sets, but we may want them to be members of some other sets. So those are what we call as atoms. And B.Math will be a set of all atoms. And then we start building in a hierarchy. It will start with V0 and then go to V1, V2, and so on. What this so on means will also be formalized. And how Vn plus 1 is defined as Vn union the power set of Vn. And again, union and power set, all of those will come from axioms. And then we keep on going against for each natural number, and then we have to define something called an ordinal number, which will be the next level of all of these. That will be the union of all. So the union of V0, V1, and so on. And then again we continue. V omega plus 1 is just V omega union the power set of V omega and so on. And this will be a hierarchy of sets. And sets are exactly those things which appear somewhere in this hierarchy. So, something will be called a set if it belongs to some BI, or B, it's a beta or something, some index. And those indexes which we are using here will be called ordinals because they are giving an order. But there is a bit of ambiguity here. So, what should we choose as our atoms? And the standard way to deal with this issue is just banish them. So there are no atoms. So V0 is just the empty set. And what do we mean by no atoms? It means that when everything that we are going to deal with will be a set. There is nothing which is not a set. So members of sets will also be sets, and their members will also be sets, and so on. So this means that we cannot talk about things like a set of flowers or something like that. These kind of things will not be allowed because members are only allowed to be sets and nothing else. You can't talk about set of humans, set of flowers, etc. But that's okay because that's not required for the formal description of mathematics. What we will require are things like set of real numbers, set of natural numbers, set of integers, etc. And this we will be able to find sets which serve this purpose pretty well. We will be able to define the set of natural numbers to be some particular set whose members you can add, subtract, etc. So these things will be sets, and that there is this notion called embedding mathematics into set theory, which is basically all the important notions in mathematics can be formulated in the language of set theory given like enough time and patience. Okay, so this is just an idea about why we need axioms and how the sets will look like once you have the axioms. Also, some of you might have heard of this notion of classes and in particular proper classes. So this is something which is not formalized in ZFC, but it is formalized as axioms in some other versions of set theory like von Neumann. And classes are basically some collections which are defined by some property, but these classes themselves are too large to be a set. Like for example, all sets, there does not exist a set containing all sets. That will come as a result of some axioms. So if you want to think of some collection of all sets, we can think of it as a class. And this is not formalized in ZFC, and instead, if we are tempted to use the word class, we'll try to rephrase it in some other way, using formulas, which is some logical terminology. So this is just something which you can keep in your mind to avoid if you don't want to use the term set, you can call it a class, proper class, some collection which is not a set. Okay, so now let's start with the axiomatic method of set theory. So this axiomatic method is not something particular to only set theory, because many of you might be familiar with Euclidean geometry, which is also built up starting from the axioms. So this is something which is ubiquitous in mathematics and used to develop many kind of systems and branches of maths, in particular set theory. And what exactly is an axiomatic method? It is basically a procedure from which we start with some axioms which are given to us, and we make logical deductions from the axioms, and then we get theorems. So we have axioms. We also have some primitive notions which we left undefined, and then we use logic, either first order logic, second order logic. So there are different versions of logic as well, which I won't be able to talk about today. But we start with the axioms, and then we get theorems, and then there is also a field called model theory, where models are built to satisfy these axioms, and we can there are many branches as well. Okay, so this is what an axiomatic method is about, and just for sake of completeness, I just want to mention the standard notation that there exists for all, and then this is negation, and the usual add or single implication and double implication. These are the standard notation come out from logic, and we also have two primitive notions. When I say primitive, I mean it's not defined. So, as all of you must have heard, it is not possible to define everything in mathematics because we have only finitely many words, and at some point we have to take some things without definition. So, in ZFC, there are two things taken without definition. One is set and one is membership, which is this. So these are taken without definition, and instead we will formulate axioms which we expect our sets to satisfy, so that we can see what we can actually do with them and what we cannot do with them. So I'll start with the axioms, and the most basic. The first few axioms are pretty intuitive, but after when I started with axioms like the axiom of choice and replacement and regularity, things will become more deep. So the beginning is pretty intuitive. There exists a set. This is the most basic because we need to make sure that we actually have something which we are working with. So this is the zero axiom. So once we have sets, we need to know when two sets can be called equal. Because equality is something which is very basic in mathematics. So this is called the axiom of extensionality, and this word extension comes from the way in which we write sets in like expanded or extended form. We are used to writing sets like this, where we list down all the members. So that makes it clear that two sets are equal if and only if they have exactly the same members. So membership is exactly what defines sets and gives them uniqueness. So in words, this axiom tells us that two sets are equal if and only if they have the same members. And in formal language, this can be written like this: for all A, for all B. So when I say for all A and for all B, there are no atoms. So everything we are talking about are sets. So A and B, whenever we use this kind of quantifiers, we're only talking about sets. So for every set A and for every set B, if this condition holds, for all x belongs to A if and only if x belongs to B. If this holds, that means A is equal to B. So this is just another way of saying that x belongs to A implies x belongs to B. If it's first from left to right, that would give us A the subset of B, and if it was only from right to left, that would give us B the subset of A. So this double implication combines both of them and it tells us that A the subset of B and B the subset of A, then A is equal to B. And obviously the other direction is true because if they are equal, they must have the same numbers because they are exactly the same. But this gives us the other implication also. And just one logical consequence of this is that if there is a set with no members, then it is unique. So why is that? Let's say we have two sets A and B, both of them have no members. Then for all x, both of these sides are false because there is no x in A and there is no x in B. So this double implication is graciously satisfied for every x, and hence we get A is equal to B. So if there was a set with no members, it would have to be unique, and that is what we call the empty set. We haven't shown its existence yet, but if it did exist, it would be unique. And the existence will come from this axiom. It is called the axiom schema of specification. So what does this word mean? It's basically a bundle of axioms. So this axiom refers to something called a formula, and for every formula there will be one axiom. So it's a collection of axioms called a schema. And this axiom tells us that for each formula, I have just noted by a dash, which doesn't contain space. It will be clear once I write the whole thing. Doesn't contain B. The following is an axiom. So basically for each formula we are having an axiom. That's why it's called an axiom schema, because it's not just one but an entire collection of axioms. So we are allowed to make use of finitely many sets here. So in logical symbols it looks like a lot of symbols, but when everything works it will be clear. So this dash is the formula which doesn't use B. So what this tells is that we are allowed to choose sets T1, T2 up to Tk and C, and for all choices of T1, Tk and C there is a set B such that for all x is in B if and only if x is in C and satisfies this formula. So this is basically giving us a subset of this set C. So B is a subset of C and any x is in B if and only if x is in C and satisfies an extra formula. So this formula could be something like x does not belong to x or x is equal to x. If you take x equal to x as the formula, this whatever B you get will be equal to C obviously. Or if you take x not equal to x, what you get will be the anti-set, because B will be a set such that anything belongs to it if and only if it belongs to C and it's not equal to itself. But there is nothing which is not equal to itself, so what we get will be the anti-set. So this gives us the existence of empty set and it also gives us uniqueness from extensionality. So just wanted to be a bit clear about what is the formula. So formula is basically a statement which you can express in logical symbols. So the most simplest formula are membership and equality. So these are the fundamental, the building blocks of all formulas. And then starting from these formulas, you can use those logical symbols like for all x or there exists x or not and or and these implications. And using these, you can build up more formulas. So for example, if you had a formula like p of x and you have another formula psi of x, p of x, then you can use these two and all of these formulas to build up more compound formulas. So this is a vague idea about what a formula is, and it can be formalized even more, but that will require tools from logic like well-founded formulae, etc.
Does the formula involve those Ti, T2, Tk?
Oh yeah, that's important. Yeah, these are they can be used in the formula. The only thing which is not allowed is B itself. The formula should not be self-referential. And you cannot say something like this. This is not valid because you're trying to define B, you're not allowed to define it using a formula which refers to itself. Okay, so just one logical consequence. Take a set C, so we know there exists a set because of axiom 0. Okay, and then using this axiom specification, we can take the formula. This dash formula can be taken as x does not belong to itself. So using this, we get. So taking this particular formula, we get an axiom. And taking k equal to 0 and all C, there exists B such that for all x belongs to B, if and only x belongs to C and x does not belong to x. So for any set C, we get a set, and let me call it BC because it depends on the set C. So the set that we got, and set builder notation, we can write it as those numbers of C which do not belong to their set. So suppose this set that we have, let's say, let us assume that it belongs to C itself. Then what happens? Suppose this is true, then either one of the following must happen. Either it must belong to itself or it doesn't belong to itself. But if it belongs to itself, since it also belongs to C, it satisfies the first condition, but it doesn't satisfy the second condition. So it doesn't satisfy the condition required for it to belong to itself. So it cannot belong to itself. And let's say it is not in itself, then it already satisfies the first condition by assumption. It also satisfies the second condition. So it satisfies the condition required for it to belong to itself. So both of these give a contradiction. So that means our assumption is wrong. So hence we conclude that this set which we get does not belong to C. So what did we get here? We started with an arbitrary set using the axiom we constructed a set B subscript C which does not belong to C. So hence for any set we can find another set which does not belong to it. So this means that there is no set of all sets. Because if there was a set of all sets it would contain itself, but that can't happen because any set, there will always be some set not in any set. Given a set, you can find something which is not in it. So there is no notion of like a universe of all sets, you cannot have that. Because you can always find a set outside any given set. So this is how the Russell's paradox is resolved. There is no paradox here. We just got something which is not in C. And another consequence is the existence of empty set which we get by just taking this formula x not equal to x. Okay, then the next axiom is the axiom of pairing. And this basically tells us that if we have two sets A and B, then there exists a set which contains A and B as its members. So if we have some sets A and B, then we have a set which contains both of them. That's what this axiom tells. So I'm just writing it in formal language. So for any two sets A and U and V, you have a set B such that if x is U or x is B, then x is B. So the simple consequence here is that we can turn this into an if and only if. And how is that? Because of axiom specification. So suppose we have two sets U and V and we got a set B such that both U and V belong to it. So there might be a possibility that this has more members other than just U and V. There might be some extraneous elements which we want to get rid of. But that can be easily solved by using this axiom scheme of specification which allows us to get a subset. If you have a larger set containing both U and V, then just take this dash to be the formula x equal to U or x equal to V, and with that you get a subset which has only U and V and nothing else. So this just gives us a potentially larger set, but you can get rid of the extra elements by specification. So it's not a big deal if you put double implication or single implication. The main thing most of the time is to get a larger set which contains what we want. Might contain extra things, but we can remove them using a suitable formula. So if we make it a double implication, then what we get is called the unordered pair. It's a set containing two given sets and nothing else. And if you just take U is equal to V, what you get is a singleton. So some consequences are that if taken into sets, you can pair them. If you take any set, there is singleton containing it. So now that we have some axioms, what can we actually do with it? So what sets do we have so far? We have this empty set which we got from there. You can put it in a singleton by the axiom of pairing or singleton and keep on doing this. You can also pair things up and keep doing this. You can create a lot of sets like this. So far these are the kind of things which we have with us using our axioms. Okay, so some more axioms, basic axioms which I just covered quickly and then move on to the other axioms. This is called the axiom of unions. So that basically tells us that if we have a set, then we can union all these numbers. So writing it in formal language for all A, then just research that more x. So once again, this axiom gives us a potentially larger set. So what is this set for? Given a set A, there is set C such that for all x, if there is a member of A containing B, if there is a member B in A which contains x, then x is also in C. So for example, if you had a set of, let's say, two things, then what does this axiom give you? Then it gives you a set C such that if there is something in, let me call this. So if there is some member of A containing x, that means if x either belongs to capital X or capital Y, then that x will also belong to C. So it's a set which contains the members of A. So again, by specification, you can get just a union and nothing extra. This might have some extra elements also, but you can get rid of them by using specification. And what we are left with is a set which contains only the members of C. And what that is denoted by union of x. Is that x belongs to C. So it's just a union of all the members. So in particular, if you have two sets A and B, then you can take C as an unordered pair. And then using the axiom of unions, you get union of members of C. But that is what we popularly call the union of A and B. So you need to have a set containing these sets and then you can union them. So you can similarly take union of 3 sets or 4 sets and so on. And there are many standard properties of union which can be proven easily. Just wanted to formalize them, like associativity and idempotence, etc. So now in union we can also generalize, like we can go from unordered pairs to unordered triples. If we have 3 sets A, B, C, then we can construct a pair, we can construct a singleton, union them to get an unordered triples, and we can go on. And another standard notion is the notion of intersection. So, what do we want with intersection? If we have, again, the same example, we have a set containing say 2 elements, and we want a new set whose members are those things which are those sets which are both in A and B. So, if we have a set of sets, any set, all of its members are also sets because there are no atoms. So, whatever is inside a set is also a set. From that, we want to construct a new set whose members are those which are present in all of the members of this larger set. So that will be called the intersection of the members of this. And surprisingly, this does not require any new axiom. Whatever we have so far is sufficient because we know that intersection of any two sets is contained in both of them. So we already have a larger set with us. Like when we want to talk about unions, the issue was that if we have two sets, there will not be a larger set containing both of them. So that larger set is what is given to you by the axiom. But here we already have a larger set which is A or which is B. So using specification on A, you can get a subset of A whose members are those which belong to A and B. And you can do the same thing for any collection of sets. So what this basically tells us is that for any set A, there exists a set B such that for all x is in B, for all any member of A, x should be in that number. So you can get this by specification of A. So it's a subset of A already. You don't need any bigger set. So this gives us intersection and all the standard properties of union and intersection. So the last intuitive axiom is the axiom of powers, which basically allows us to take power sets. And what this tells us is that for any set A, there exists another set B such that for all x, So what is this thing telling you? Just telling you that x is a subset of A. Because whenever something belongs to x, it must also belong to A. So this is just a logical way of writing that x is a subset of A. So what this axiom tells you is that it gives you a set B, so that whenever x is a subset of A, it's in B. So B contains all subsets of A. And once again, it might contain extra things which you don't want. You can get rid of them by specification. Once you have a larger set, you can remove the unnecessary things by specification. And once you have removed extra things in B, there might be things in B which are not subset of A. Just remove them by taking a suitable formula. And what you get is called a power set of it. So now with some extra axioms, we can construct more sets than what we have there. We can construct unions of sets, we can take power sets, etc. So far we have seen the most basic axioms. The axiom 0 says that there exists a set. Axiom 1 is extensionality, which tells you when two sets are equal. Axiom 2 is specification, which allows you to get subsets. And axiom of pairing is allows you to pair two sets. You can take unions, you can take power sets. And with these axioms, they are sufficient to do basic algebra on sets like union, intersection, and then there are also many laws like commutativity, associativity, etc., using which you can define things like Boolean rings and etc. So these axioms are enough to do basic set algebra. And there is also the famous De Morgan's law, which helps us go from intersection to union by taking complements. And that gives us a notion of duality. If you have some result involving unions, you can complement everything and get a result involving intersections.
So have we defined complements yet?
Yeah. Complements also can be defined using the diagram specification, and that's a notion called relative complement. So one thing to keep in mind is that there is no notion of absolute complement. What does absolute complement doesn't make sense. Why is that? Because let's say you want to define, you have a set A and you want to talk about all those elements which do not belong to A. Let's say this was actually a set. And what would happen if you take A union B? It will contain all sets. But that is not possible because I already proved that given any set there is something not in it. In some set it is not in it. So you cannot have a set of all sets. And there is no notion of absolute complement. You can't talk about all sets not in a given set. But you can talk about relative complements. You can talk about all sets which are not in A but in B. And this is once again just a subset of B which you can get by specification. It's written in segmental notation and it's just this. Just a subset of B. This makes sense. And often we talk about complement without mentioning the larger set, and in such cases the larger set is understood. Like it might be the real numbers or some space where we are working in. In that case, you can just ignore B minus A and just write A complement. It's understood that we are talking about relative complement with respect to some larger set, which is fixed in the background. Sometimes it's called an ambient space or something like that. Okay, now let's move on to the next important notion of ordered pairs, using which we can define relations and functions a bit more formally. So, what is an ordered pair? Basically, given two sets x and y, we want to construct a new set out of this. For now, I'll just denote it with this kind of notation, this standard. But we want some set like this which satisfies this property. This is true, then we want x to be equal to x1 and y to be equal to y1. So this is we want something which takes into account the order. The first coordinate should be equal to this, the first coordinate, second coordinate here should be equal to the second coordinate here. So we want to construct some set out of two sets which has this property. And there are many things which you can think of initially. You can maybe think of this, but this obviously does not work because this doesn't take into account the order. you can put this is the same thing as this. So this does not work, and there have been many attempts to define suitable candidate for this, and the most standard one is by Kuratowski, and it is this is the definition which we will follow. It doesn't really matter what exact definition we follow, but better to have some standard things. We just need this property to be satisfied. So this is the definition of ordered pairs by Kuratowski, and it's a nice exercise to check that this satisfies this condition. So if this thing was equal to the same thing, but x is replaced with x1, y is replaced with y1, then you can show that x1 must be equal to x must be equal to x1 and y must be equal to y1. So this is the standard definition of ordered pairs. So there is some unintended consequences also. This has the required property, but it also has some redundant properties. Like singleton x belongs to the pair x comma y. This unordered pair belongs to the ordered pair. So there are some redundant consequences also, but those are fine. There are some extra properties which we are getting, but you can just ignore them. And you just need that particular property that it preserves the order, takes into account the order. So once you have ordered pairs, you can define Cartesian products. So everyone is familiar with this notion of A cross B. So it's the set of all ordered pairs of the form x comma y, where x is in A and y is in B. So that's something we're all familiar with. The only problem is that how do we make sure that it's actually a set? How do we know that there exists a set of all ordered pairs with x in A and y in B? So the way this is remedied is with this particular lemma. The goal is to get a larger set. We want some bigger set which contains all ordered pairs like this. So how do we get that set? We already know that because x is in A and y is in B, x belongs to A union B and y also belongs to A union B. So with a bit of simple manipulation, you can check that this ordered pair actually belongs to the power set of A union B. Because this is a set of two sets, where this is a subset of A union B and this is also a subset of A union B. So you can just write it down and check that this property is satisfied. So we get a larger set which contains all such ordered pairs, and once you have a larger set, you can use specification to get rid of the unnecessary elements, and what you are left with is a set containing only such pairs, and this is what we call the ordered Cartesian product of two sets. So there is also this standard notion of relations and functions which everyone is familiar with. So the only thing which wasn't defined so far was the notion of ordered pair, and that has been defined like this. Once we have ordered pairs, we can talk about Cartesian product and then relations and functions. Relation is any set whose all of its members are ordered pairs. Any set of ordered pairs is called a relation, and if some ordered pair belongs to the relation, we just say that x is related to another relation. And functions are also special relations which have a special property that for if x is related to two different elements, if this belongs to f, the function, and x comma y2 also belongs to the function, this must imply y1 is equal to y2. So just a standard notion, just a new thing here was the definition of ordered pairs, and we can again talk about injective functions, surjective functions, bijective functions, and etc. And it's just a simple exercise to think of, if you have a relation, it's a set of ordered pairs. So can we talk of the set of first coordinates, which is called a domain? Does there exist a set which contains only those sets which appear as first coordinate of something in R? Those are some simple questions which you can think of. It all boils down to finding a larger set. And similarly in functions, you can talk about the image, the range of the function, which is the set of all second coordinates. And once again, it boils down to getting hold of a larger set which contains whatever we want. and then we can get rid of the unnecessary things using specification. So this is how some basic things are formalized. We just need to show that those things are actually sets. Okay, and then similarly we can generalize to like ordered triples can be defined like some sort of we just look at ordered pair and then just a ordered pair where one member itself is an ordered pair. And using this you can define like n linear relations or the Cartesian product of more than two sets. But all this can be done only in the finite case when we have finitely many members. And what exactly does finite mean, that will be formalized soon. But to generalize the notion of Cartesian product, we will be using functions. I'll introduce that soon. But before we go into that, I want to talk about the construction of natural numbers. So under relations we have special relations like equivalence relations, ordering relations, etc., which everyone is familiar with. So there is nothing much theoretic about that. The only thing was the definition of ordered pair. Okay. So before the construction of natural numbers, just one thing. I just want to give a short motivation for the axiom of choice and talk a bit about it. So let's say f is an injective function. So we all know that injective functions, they have left inverses. Let's say f is from x to y and g is from y to x, such that g of f is the identity function on y, on x. The input is from x. So we know that injective functions always have left inverses, and how do we prove? It's easy to prove that because what we need is g of f of x should be equal to x for all x in bracket. So because it's injective, every member in the codomain in the range has a unique pre-image. So we can just set f of something in the image to be the unique pre-image, and we can define g arbitrarily outside the range of f. So we don't have to make any choice here. We don't have any choice, but everything in the range is a unique pre-image. So there is no problem about which pre-image to choose. But there is a problem when we are talking about subjective functions. Let's say f is a subjective function from x to y. So this has the injective function has a left inverse, then it's a natural question, and subjective function would have a right inverse on y. So what do we have to do in order to construct the right inverse? What is required is f of g of x should be equal to x for all x in y. Or in other words, g of x has to belong to the inverse image of this singleton. But because it will not be injective, this inverse image will always be non-empty because it's surjective. But it cannot be injective, so the inverse image cannot be a singleton. It might even be infinite, uncountable, uncountable, whatever. So the problem is we have to make a choice every time. For every x, we have to pick some element from the inverse image of singleton of x. And it turns out that this cannot be done using the axioms we already have. We cannot prove that there exists some g such that for every x, g of x is something in the inverse image of singleton x. And it has been proven that, so this is basically we have to make choices over here. And we need to make infinitely many choices. We can't write it down using logical symbols because logical language is always finitely long. So that's why we need a new axiom here, which is called the axiom of choice. And this is something which has been proven to be independent from the remaining axioms. So what does it mean to be independent? It means that there exists some model which satisfies the remaining axioms, but it does not satisfy this. And there also exists a model which satisfies the previous axioms and satisfies this. So it doesn't matter whether we take this to be true or false. There will not be any inconsistency unless there was already an inconsistency in the previous axioms. So this axiom of choice is something which allows us to say the existence of a choice function. So I hope this gives you some motivation about why we need to be able to choose things. This happens a lot of times. So this has many forms. So one version of this, first form will be that if R is a relation, there exists a function x which is a subset of R with the same domain as the relation. So what is this function doing? It has the same domain as the relation, but the relation might be multiple valued. It might take different, it might relate the same x to multiple y's. Like for example, each x, you can take a relation where x comma y is there in the relation. Different only if x belongs to the inverse image of y. Okay. So what we want to do is we want to choose one of the images of x, and that's exactly what this function is doing. It is single value. So for each x, it assigns a unique y, which is one of those y's which is assigned under R. So this is one formulation where we are taking one image for each x in the domain, and there is another formulation. For that we need to define Cartesian products. So we want to define arbitrary Cartesian products. So if we have some indexing set I, and we have a function, let us write it down. So here h is some function with domain I. So that basically assigns one set h of I to each member in capital I, and this Cartesian product is a set of all functions whose domain is I, and for any I in the domain, f of I belongs to h of I. So f of I is basically picking one element from h of I for all I. So it's in some sense a choice function, and this Cartesian product is the set of all choice functions. So the second version of the axiom of choice tells us that this Cartesian product of h of I is non-empty if each h of I is non-empty. So that means that there exists at least one function f whose domain is I, and for any small I in capital I, f of I belongs to h of I. So this function f is basically choosing one element from every h of I. The axiom of choice basically gives us the existence of such a function, but it is not constructive. We do not know what that function looks like. And surprisingly, this axiom has a large number of equivalent formulations. There are many surprising ones. The most important one is called Zermelo. So Zermelo basically tells us that if you have a partially ordered set, so what is a partially ordered set? It is just the set of the relation R, where this relation satisfies three properties. It is reflexive, antisymmetric. Reflexive as in every element is related to itself. It's antisymmetric, meaning if x is related to y and y is related to x, that should imply that x is equal to y. And it is also transitive. This is just similar to how the containment relation, subset relation works for sets. These three properties are what containment holds. If A is subset of B and B is subset of A, then A is equal to B. Every set is a subset of itself, and transitability also holds. So this is just abstracted to give a general notion called coset. And this Gauss lemma tells us that if A is a non-empty coset and every chain has an upper bound, so a chain is basically a subset of the coset where any two elements can be compared. It's called partially ordered because there might be two elements such that neither x is comparable to y or y is comparable to x. Like for example, we take these two as subsets of real numbers. This is not a subset of this and this is not a subset of this. So we have two numbers which are not comparable. So chain is a subset of the coset where any two numbers are comparable. So if every chain has an upper bound, an upper bound is some number in the original coset which is comparable to everything in the chain and greater than or equal to all of them. So this upper bound need not belong to the chain itself, it has to belong to the coset. For example, if we had a chain like the set containing 2 and set containing 2, 3 and we keep on going, then an upper bound would be the union of all these. That is one potential upper bound, but that is not a number of the chain.
Upper bound is just set.
Yeah, it's some number of the coset which is comparable to everything in the chain and it is bigger than or equal to everything in the chain. Then there is at least one maximal element. And again, what does the maximal element mean? Maximal element again is something in the coset such that nothing is strictly bigger than it. It may not be comparable with every element, but if it is comparable to something, then it must be bigger than that. So this is what Gauss lemma tells us, and it looks really different from those formulations. And it's very nice to think about how this is equivalent to that. So this is much more useful than that formulation in many situations because there are many scenarios where you want to have a maximal element, like if we are dealing with group theory or ring theory, we want to find maximal ideals or maximal subgroups. And even in linear algebra, if we have a vector space which may not be finitely dimensional, then this can be used to show that there exists a basis, because a basis is basically a maximal linearly independent set. So if you take the coset to be the set of all linearly independent sets, you can just show that it satisfies the hypothesis of Gauss lemma, and hence it has to have maximal element, and that will be a basis. So this version is really useful, and there are also some other very surprising versions which I will just state it now, but I will write it down later if I have time. And one of the versions is that any set is equinumerous to its Cartesian product with itself. Equinumerosity basically means there is a bijection between any infinite set A and its this is also equivalent to Gauss lemma, and there are many other versions like any connected graph has a spanning tree, etc. So you can find many of them online and think about how they are equivalent, or at least through one direction of the integration. So this is some information about the axiom of choice. Now let's move on to something bit different, which is the construction of natural numbers. Okay, so natural numbers is something which is fundamental to mathematics, and once we have natural numbers, we can construct many other number systems out of it, like the integers, and then the rational numbers and the real numbers. So once we have the natural numbers, we do not need any new axioms to make new number systems. But for natural numbers, there is an axiom which is used for proving the existence. So the idea behind this is that we want to make some numbers system to count. So let's say we start with the empty set as the label for the, let's say we want to count something. And we want to be very minimalistic. So as a label for the zeroth element, we use the empty set. So now we want a label for the first element. And as we want to be very minimalistic, we just take the new label to be the set containing the old label. So this is the label for the first element. And to make the new label for the second element, we just take a set containing the old labels. And we keep doing this. So the label which we are creating to count the next element is just a set containing all the previous labels. So it's a very minimalistic idea, and we are trying to use as less as possible to construct the natural numbers. So here basically the operation which we are using to go from one label to the next is called the successor operation. So we a successor of A is denoted by A plus, and we write it like this. It's just whatever was done before, union with the singleton of A. So this A plus has just one more element, which is A itself. So you can see that A is the subset of A plus, and A belongs to A plus. Both. And under this, we want the set which is closed under this operation of successor. So natural numbers, any given natural number is successor is also a natural number, right? So we want to get a set which is closed under this operation, and such a set is called an inductive set. Inductive set is set A that satisfies this property that the empty set belongs to it, and whenever it has a number small a, and successor also belongs to it. So this is the definition of an inductive set, which is how we try to model natural numbers. But right now the problem is that we don't know if the inductive set exists or not. So that's why we need a new axiom, which is called the axiom of infinity, and it just tells us that an inductive set exists. And once we have at least one inductive set, we can now talk about the smallest inductive set, which is what we call the set of natural numbers. So we have the next axiom, axiom of infinity. Just say that there exists an inductive set. So once we have at least one inductive set with us, we can talk about the smallest inductive set. So this is a very nice idea in set theory that we do not know, we just know that there exists an inductive set, but we don't know how it looks like. So we cannot study the inductive set given to us by the axiom. So instead of studying that, we define the smallest inductive set, and what we mean by smallest is that we can't actually take the intersection of all inductive sets, because there cannot be a set containing all inductive sets. To take intersection of some sets, we need to have a set containing all of them, which may not be the case. So what we do instead is, let's say the inductive set given to us by the axiom is denoted by capital A, then we define a set called omega. It is this the smallest inductive set. And how do we get that? Because it's the smallest, it's going to be a subset of A, right? So we can apply axiom specification on set A, and we can call omega to be the set of all elements which are already there in A, and X belongs to B for any inductive set B. So I am writing this in words, but it is possible to write it in formal language, because the very definition of inductive set is already written in formal language. So we want to collect those elements which are in A, and they are also in B for any inductive set B. So I'm not writing it as intersection of inductive sets because there cannot be a set containing all inductive sets. But this is a way to get around it and to get hold of this smallest inductive set. And this is what we call the natural numbers. And by very definition, it satisfies induction principle. What is induction? Induction is basically if you have a subset of omega, subset is inductive. What does inductive mean is the standard notion of induction. It contains the empty set which is 0, and whenever it contains some natural number n, it also contains the successor of n. That is the standard notion of induction. So if B is inductive and it is a subset of omega, then B is equal to omega. So this is exactly what we call induction. If you have a subset of omega which satisfies the property that if it contains 0 and contains n, then it contains n plus 1, then it must be equal to omega because omega is defined to be the smallest set with this property. So if there is something smaller, it must be omega itself. So by definition, we get induction as a principle because of the very minimalistic way in which we define omega. Induction comes out as a direct consequence. So there is also this notion of recursively defining a function. It's called the recursion theorem. This is another important theorem which we use all the time. And basically, what the idea is that if we have a function, if we have a set A is a set and some small a belongs to capital A, and that is the function and A to A already given to us, then there exists a function h from omega to A such that it satisfies the property that h of 0 is equal to A. 0 is nothing but the empty set, and for every natural number h of n plus is equal to f of h of n. So it's basically what we think of as inductive definition. We are defining the value of h at n plus as some function of the value of h at n. So this is what we call recursion theorem, and this has a very nice proof, and the idea of the proof is to use like approximating functions. We take functions whose domain may not be the whole of omega, but it has maybe some finite domain, but on that domain it satisfies this property. So showing existence of those functions, approximating functions is easy, and then we do some work on those approximating functions, and we take the union of all of them, and the union of all the approximating functions will be this. It's something like taking a function which converges to the one we actually want. So I won't be able to go through the proof, but it's a nice idea of using approximating functions. Okay. So once we have this recursion theorem, we can now define operations on natural numbers like addition. So we for any n in omega, we can define addition by n such that it satisfies the property it takes 0 to n. So here in place of capital F, we are taking the successive function, and we are recursively defining the function am, which is nothing but addition by m. It sends 0 to m, and it sends n plus to the successor of what it sends n to. So nothing but n plus 1 is equal to n plus n plus 1. So this gives a recursive definition of the addition, and now we can define addition to be a binary operation. And similarly, we can recursively define multiplication and exponentiation as well. So how do we define multiplication? It's just am of 0 is 0 and am of n plus. Am of n plus to be some function of am of n, and that is nothing but am of n plus n. nothing but n times n plus 1 is n times n plus m. This is how multiplication can be defined, and similarly you can think about how exponentiation can be defined recursively. So we are just defining the value of the function at n plus as some function of its value at n, where the function is a successive function which takes a to a plus. And finally, when we define natural numbers, like basically natural numbers look like this. This x will be the successor of this, which will be just adding a new element, which is itself. This is added to get this, and so on. So we observe that this is contained in this is contained in this, and so on, and also a subset. So we exploit this property to define ordering of natural numbers. So we define n to be less than n if n belongs to n. So the definition of natural numbers gave us this extraneous property that smaller natural numbers, what we wanted to be smaller was the member of what we wanted to be bigger. So we just exploit that and use it to define the order. And now, of course, we have to prove things like no natural number belongs to itself and things like that. And such results are usually proved by induction, and that shows us that this definition of ordering actually makes sense. And by induction, you can prove that this operation is compatible with addition, that if n is less than n, then n plus k will be less than n plus k, and it's also compatible with multiplication and so on. So all those are some basic results which can be proven using induction. So this completes the section on natural numbers in just an overview, and also natural numbers are well ordered by this relation. And what well ordering means is that if you have any non-empty subset, it must have a smallest element. So this is another result which is proven by, it can also be proven using from axioms, and this is a result which we also use all the time, and this is also done by considering using some sort of induction. So you can look up this, you can try proving this later. So once we have defined natural numbers and shown that they have nice notion of ordering, addition, multiplication, and etc., we can use this to now define other number systems like integers. Integers are defined as equivalence classes of pairs of natural numbers which satisfy some equivalence relation. And then similarly, we can go on to define rational numbers as like equivalence classes of integers. As think of a ratio as an ordered pair and define some equivalence relation on that. And then we can also move on to real numbers. So those do not require any new axioms, because the only new axiom required here was the axiom of infinity, which gave us that there was at least one inductive set, and from that we are able to build all this theory to define all sorts of number systems. So, and then we can move on to complex numbers, etc. So once this is done, we can also define ordering relations on all these number systems that we create. Now I can move on from number systems to the next topic. So this is another fundamental topic in set theory which allows us to compare two sets. So we say that set A is equivalent to B if there exists f from A to B which is bijective. This is the definition, and it's easy to show that if A is, any set is always equivalent to itself and it satisfies the symmetry, because it is and because you can compose bijective functions, you can show that it also satisfies transitivity. So this is how equinumerosity is defined. And this is the most general notion. If we have some particular structure on the set, like for example, if we know that the set we're talking about are both subsets of natural numbers, then there are other ways of defining this notion of size, like using natural density and things like that. Or if you're talking about real numbers, you can define size using the notion of measure. But those cannot be done in general when we do not know anything about the two sets. If we don't know anything, if we don't know any structure, in that case the only way is to define it like this. So some basic results here are that any set A, power set of any set is equinumerous to 2 power A, where 2 power A is just a notation for set of all functions from A to 2. And 2 is nothing but the set containing 0, 1. That's how we define any natural number. It was the set of all smaller natural numbers, like the small set of all the labels which we already used. So it's very easy to see this result. You just take any subset and you make a function which sends something to 1 if it's there in the subset and something to 0 if it's not in the subset. Basically the characteristic function. And then the other standard result called Cantor's theorem, which says that there does not exist a subsection from any set to its power set. And this is also a very neat result, and the idea for this proof is consider any function from A to P of K, and we will now be able to construct something in over here that does not have preimage. So just look at the set of those elements in A which are not contained in the image element F. So this can be shown to be a set using specification, and you can, with a bit of case work, you can easily show that F has no preimage. So this is something like a diagonalization argument, where you look at the diagonal, those which are not contained in their own image, and you can show that this set does not have preimage under this function. Given any arbitrary function from E to power set of A, you will be able to find some set which has no preimage. So this gives us that given for any set there is something bigger than it in some sense. And Fraenkel also proves using the famous diagonalization argument that natural numbers are not equinumerous to real numbers, and that is also another famous result. Okay, so now we have defined equinumerosity. Let's actually define what finite sets are. Okay, so a set is said to be finite if it is equinumerous to some natural number. This is the definition of finite sets. There are also alternate ways of defining finite sets by saying that a set is finite if and only if it is not equinumerous to any proper subset of itself, and that comes as a consequence of this definition. And with this definition and using the properties of natural numbers, many standard results can be easily proven. Like as I said, a no natural number is a subset of a no natural number is equinumerous to a proper subset of itself. That is one of the standard results called the Pigeonhole principle. And using this, it follows that if any set is equinumerous to a proper subset of itself, then it cannot be finite. And then that is what we call as infinite sets, which are not equinumerous to any natural number. And it can be shown once again that omega is not finite. These are all some basic results under this topic of equinumerosity, which you can explore further. Omega, which is a set of all natural numbers, is not equinumerous to any natural number. And also for this, to introduce the notion of cardinality, we first prove there is a result that any finite set is equinumerous to a unique natural number. So if any set is equinumerous to two natural numbers m and n, then m must be equal to n. So in some sense, for finite sets, we can use natural numbers to talk about their size. If a set is finite, then there is a unique natural number equinumerous to it.
Only function implication should be 0.
Yeah, if n is equal to n, okay, yeah. If we know that it's equinumerous to two natural numbers, then they must be equal. Right. So now we try to generalize this notion of size of a set with this concept of cardinality and cardinal numbers. So what is cardinality? Like basically you showed that this notion of equinumerosity is a kind of like an equivalence relation.
Why did we remove the if not if condition?
I mean, we do not know that A is finite already. If it is equinumerous to two things, then they must be just.
But even if it's not finite, both m and n are finite.
Okay, just add an extra condition. Suppose A is finite, then we can say this. M is. Wait.
Still m can be anything.
Okay, let's say that A is given to be equinumerous to some natural number in omega. Let m belong to omega. Then we can say that A is equinumerous to m. Different on A, m is equal to m. Now it makes sense. That basically means that no set can be equinumerous to two different natural numbers. That gives us the notion of uniqueness of size, so that we can talk about size of finite sets in terms of natural numbers. So we know that equinumerosity is equivalence relation. It's not actually a relation, so I'm putting it in within quotes, because equinumerosity, the relation concerns all sets, and for something to be a relation, it must be a set of ordered pairs. So since this relation concerns all sets, we cannot. It's not actually a relation, because if you look at the set of all like ordered pairs A comma B, such that A is equinumerous to B, this we can show that this is not actually a set, because it will be it end up containing every set. If this relation is actually a set, then its domain would end up containing all sets, because all sets, any set is equinumerous to some other set which is itself. So it's not actually a relation, but it still satisfies the conditions of like symmetry, reflexivity, and transitivity. So in some sense, we have like equivalence classes of under equinumerosity, and we want to pick one representative from each equivalence class. So we have one class of, let's say, all finite sets, all sets which are equinumerous to let's say one sets, all things equinumerous to 1, and then we might have all sets equinumerous to omega. These may not be sets, but at least they are classes, and from each of them we want to pick one representative. So from here we can pick 1 as a representative, from here we can pick omega as a representative, but in general we want to pick one representative from each class. And to do this, we will require some other notions. We will first define. We need this axiom called the axiom of replacement, which will allow us to construct something called ordinal numbers. And once we have ordinal numbers, there will be something which is well ordered. So there will be a notion of a smallest ordinal which is equinumerous to a given set. So once we have the notion of smallest ordinal, we can just pick that as a representative. So now let's move on to the notion of ordinal numbers. So before that, and before I define cardinals rigorously in terms of ordinals, let's just assume for now that cardinals have been defined, as in for each equivalence class we have picked one representative. Then we can talk about cardinal arithmetic. So we can just a brief notion of how it looks like. If we have two cardinals, So these cardinals are basically what we have chosen to be the representatives of certain equivalence classes. And how we will be choosing them, I will tell you that very soon. But before that, cardinal numbers are exactly the representatives which we have chosen using some method. And once we have chosen them, we can do operations on them. So we can define addition of cardinals. That will be defined as let's say K is equal to the cardinality of some set capital K. Card is just a notation for cardinality. Just means that whichever class this set belongs to, this was chosen as the representative of that class to represent its cardinality. And let's say some lambda is the cardinality of some other set, then K plus lambda is defined to be the cardinality of the union of capital K and capital L. Just a small exercise to check that this is well defined. Well defined in the sense that instead of K, if you pick K dash to be another set with the same cardinality as K, instead of L, if you pick L dash to be another set with the same cardinality as L, then this should be equal to the cardinality of K dash using L dash. So that's what I mean by well defined. And similarly, you can define the product of cardinals to be the cardinality of the cross product. And you can also define exponentiation to be the cardinality of the set of all functions from L to K. This is the notation, which is quite standard. Set of all functions from L to K. And even these two can be checked to be well defined. So it doesn't depend on which K we pick from that class. And once we have this, many properties of cardinal arithmetic follow, which you can look up. Like for example, it will be commutative, it's associative, and it satisfies the properties of distributivity, etc. So this is the beginning notion of how cardinal arithmetic looks like, and you can read up more on this. Okay, so now let's move on to the notion of ordinals. And ordinals is something which we use for studying well-ordered sets. So let's see what is a well-ordered set. Basically, a well-ordered is a particular kind of relation which satisfies the condition that every non-empty subset has the smallest element. Well-ordered set A is a linear total ordering. Total ordering basically means that any two members need to be comparable, so it's not just a partial ordering. So for example, this total ordering could be something like a strictly less than or strictly greater than, or like subset is not equal to. These are all examples of total ordering. So either given any two element, there should be this notion of trichotomy. Either x is less than y, or x is greater than y, or x is equal to y, and exactly one of them should hold. And obviously, reflect transitivity always is there. And so well-ordered set is some particular type of ordering where any non-empty subset has the smallest element. For example, natural numbers have this property. So another nice consequence of the John's lemma is that any non-empty set can be well-ordered. Each set can be well-ordered. It comes from John's lemma. why exactly do we need to study well orders? That's because it always, you can in some sense list the elements in some kind of order. So if it have any, since the whole set itself is well ordered, say A is a well ordered set. Since the whole set itself is well ordered, it has the smallest element T0. And you can remove T0 from A, and since A minus T0 is also non-empty, you can again find the smallest element T1. And you can keep doing this. Remove T0 and T1, you are left with the non-empty set, then find the smallest element. You can keep going like this for each n. If A has sufficiently many elements, and for each n you can define Tn. And after defining Tn for each natural number, you may still be left with more things. So remove all of them, and then whatever you are left with will again have a smallest element, which we denote as T omega. And once again remove T omega, the remaining subset will have a smallest element. You can call that T omega plus 1 and so on. So there is some proper good notion of order, and the subscripts which we are using here are what we will be defining as nominals. So in some sense we want some labels, like how we saw natural numbers as labels. We want to label the members of the set. And it's once again the same kind of idea. Use the empty set 0 to label the smallest element, and then to label the next element, just take the set of all smaller labels. It's a very minimalistic idea. So we already made some labels, put them in a set to get your next label. So what would be omega then? It's the set of all labels which have been used so far. So it is just all the natural numbers. I'll just write them using this decimal notation. So what would be omega plus 1? The set of all smaller labels. So we have all natural numbers and omega. And it keeps going like this. So in order to actually formalize this, we will need a new axiom called the axiom of replacement, which I will tell you soon. So in order to define organisms, we need this notion of transfer and reduction. And what it tells us is that if you have any formula as in some statement which you can write using logical symbols, then the following will be a theorem. Once again, it's a theorem schema, so it's a collection of theorems, which means for every formula we get one theorem. And what theorem says that, write on the next book. So let's say this is a well ordered on some set A, and assume that for any f there exists unique y such that gamma f comma y holds. So gamma is in some sense like a function. To each f it is assigning a unique y such that gamma f comma y holds. But you can't exactly call it a function because it's talking about any f. So its domain contains all sets. So if we cannot think of it as a function, we can call it as a function class. But in ZST, classes are not formalized, and this is how we reword it. We reword it in terms of formulas. This is a particular kind of formula which is kind of like a function, but its domain has everything, every set. There exists a unique function capital F with domain A such that, and there's a notation here which I will define. So what is this segment of T? Segment of T is just collection of all things in A which are less than T. So that's the initial segment of A until T, collection of all small elements. So what exactly is this function doing? So we have defined f for all elements which are less than t. Using that, we are defining f of t such that the formula satisfies this. So this formula is in some sense assigning for anything a unique element y. So f of t is what gamma assigns to f restricted to segment t. So to prove this transparent recursion schema, it cannot be done using the axioms which we already have, and for that we require a new axiom, which is called the axiom of replacement. I'll finish in 15 minutes. Okay, so this axiom is called the replacement axiom, which is another important axiom in literacy. So when we have a function, the range of the function can be proven to be a set. It's a set of all images under the function. But we want to extend the same notion to a formula. The formula is bigger than a function because its domain contains everything. So under a formula, there's a notion of y being the nominee. Y is the nominee of f. F nominates y under gamma. That's how you can read this. So this gamma satisfies a special condition that for any f it nominates a unique y. So for special kind of formulas like this, like for example gamma of f comma y could say something like y is equal to the range of f. So clearly for any f gamma nominates a unique y which is the range of f. So for such kind of formulae, if we have a set a bit lengthy to write and logical symbol. I'll just explain this one. Okay, so what is this telling us? We have a particular kind of formula which is like a function class. So if there are y1 and y2 such that x nominates y1 and x nominates y2, then y1 must be equal to y2. So any x has a unique nominee. So if this formula satisfies this uniqueness condition, then for any set A, if we replace everything in the set with its nominee under P, so there exists a set B such that y is in B if and only if it is the nominee of some x in A. So this is what this replacement tells us. So basically we have a set A, we replace everything in A with its nominee under this formula. So this collection of nominees will also form a set. That is what this axiom tells us. It is stronger than just saying that range of this function is also set, because this is more than a function, because it tells something nominates something for any x, for any set x, not just the members of some given set. Okay, so now that we have this replacement axiom, using some methods like by taking approximating functions, we can prove this transparent recursion theorem, which allows us to somewhat extend the definition by induction. This is something which we do for natural numbers that can be extended beyond the natural numbers, and that will allow us to define ordinal numbers by taking this gamma x comma y to be a special formula which says that y is equal to range of f. And using this we can define this important notion of epsilon images. And let me do that. So let less than be a well-ordered on a set A. So just take the same formula, gamma of f comma y is equal to range of x, y is equal to range of f. Then by the factorization theorem, we get a unique function that satisfies this property. And let's actually unfold what this looks like. So let's take T0 to be the smallest element of that well-ordered set. So segment of T0 is empty because there is nothing smaller than T0. So this will be range of T restricted to the empty set, which is empty. So, and this can be written as the set of all f of x such that x is less than t. So this is exactly the idea which we use to construct the labels. The new label is a set of all small labels. That's it. So E of t1 will be the f of x less than x such that x is less than t1, which is just E of t0, which is the empty set, and it will keep going. E of t omega would be the set of all f of x such that x is less than omega. Those are just exactly the natural numbers which are less than omega, contained in omega. That will just be like empty set, which is E of t naught, and then the set containing the empty set, which is E of t1 and so on. So this is how ordinal numbers are formalized using this notion of epsilon images, because it's made under this kind of containment. You can see that this is contained in this, this is contained in this, and so on. The main idea is like to go on creating new labels based on the already existing labels and putting them in the set. So these ordinal numbers have very nice properties because they have been defined to like label the members of a well-ordered set. It can be shown that ordinals themselves are well-ordered. So these are all. So how do we define ordinal? Ordinal of A is defined to be the image of this function. We have this function E, right? So E is called the epsilon image. Epsilon is just the term for this membership symbol. Epsilon in the range of E is called the epsilon image of this well-ordered set A comma this. So for any well-ordered set, we can assign an epsilon image, and that epsilon image is what we call the ordinal of the well-ordered structure A comma E. So given any well-ordered structure, we can assign an ordinal to it, which is nothing but the set of all labels, which are being used. Set of all E, everything in the range of E is the label. So the collection of all of those labels is the ordinal of the well-ordered structure. And every time we are making a new label, we are just collecting all the smaller labels and putting them in a set. So that's a very neat idea of making labels for arranging the elements of a well-ordered set in models. So once we have these ordinals, we can prove with many nice properties regarding them, like any set of ordinals will have a smallest element, etc. And in particular, we can define cardinal numbers now. Cardinal number of any set A is defined to be the smallest ordinal between numerous to A. So that is how we define a cardinal number. So basically, while defining cardinal numbers, the main thing was from each class of equinumerous sets, we have to pick a representative. If the sets are finite, we pick the representative to be the unique natural number in that class. But if they are infinite, then we choose the smallest ordinal in that class of equinumerous sets, and we define that to be a cardinal. So the smallest also makes sense because we can show that any if you have some ordinals which satisfy a formula, then there will be a smallest ordinal satisfying that formula. and in this case that formula is being Q inverse to A. Just take this Q inverse to A as a formula, and you can prove that there exists the smallest ordinal satisfying any given formula. Using that, this definition of cardinals makes sense. Okay, so just I want to give a brief about how to formulate the hierarchy which I introduced in the beginning, and with that I will end this talk. Okay, so if you remember that hierarchy that we had, we had B0 to be the empty set, B0 to be contained, it was B0 to be, you can show that it is the power set of this. It was actually B0 union the power set of B0, but this is empty, so it is just power set of B0, and we keep going like this, and then we define B omega to be like the union of Vi from 0 to infinity. So this was the kind of hierarchy. So we wanted sets to be exactly those things which appear somewhere in the hierarchy. So given any set, we need to have some V alpha such that X contains that V alpha. So there is this notion of set being grounded. It should be contained in some V alpha, and it turns out that this is also cannot be proven using the axioms. But obviously, we really want this to be true. We want sets to be we want all sets to appear somewhere in the hierarchy. So for this, it turns out to be equivalent to an axiom called the last axiom of ZSP. It's called the axiom of regularity. And what it says is that for all sets X, if X is non-empty, then there exists Y belonging to X such that Y intersection X is empty. So any set, non-empty set, has a member which is disjoint from that set. So this is called the axiom of regularity, and it's very interesting to think of how this and this are equivalent. In order to define this hierarchy, we use transparent recursion, which you can read about how exactly this hierarchy formalized. And once you formalize it, it's a very nice thing to think about where this equivalence comes from. So usually the axiom of regularity is stated in this form. So it's not, because that's just a shorter way of writing the same thing. But it actually comes from wanting to show that every set is grounded. And some nice consequences of this axiom of regularity is that there does not exist a function from omega to some set x such that f of n plus 1 belongs to f of n for all n in omega. Why is that? Let's say such a function existed. So just look at its range. It has f of 0, f of 1 is contained in f of 0, f of 2 is contained in f of 1, and so on. So this thing, this set f of 0, f of 1, f of 2, does it have a member which is disjoint from this? Let's call it f. Is there a member of f which is disjoint from f? F of 0 is not disjoint from f because f of 0 contains f of 1, f also contains f of 1, so they are not disjoint. F of 1 is not disjoint from this because f of 2 is there in f of 1, f of 2 is also there in f. So in this way, by induction, you can show that no member of this is disjoint from it, which contradicts the axiom of regularity. So you cannot, in some sense, have a chain like this where the right one is contained in the left one. And in particular, you get this result that you cannot have two sets A and B so that A belongs to B and B belongs to A. Because if it did, then you can just construct a chain like this. A belongs to B, B belongs to A. You can just go on like this, alternating between A and B, and you get a chain like this which is not allowed. And in particular, you cannot have A belongs to A. Because if you did have that, you can construct a chain like this, which is again not allowed by the axiom of regularity. So thus we get that no set is contained in itself as one of the consequences of the last axiom of regularity. So this is a very interesting thing which I wanted to just introduce so that you can read more about all this, and also read about ordinal arithmetic and some other interesting topic. I just wanted to mention some references. So the main references which I followed were almost a very famous mathematician. He has a nice short book called Nine Set Theory. It's called Nine, but actually it's also axiomatic, but not completely formal, but it can be formalized. And another important book which I followed was a book by Anderton called Elements of Set Theory. Elements of Set Theory. This is a very amazing book for a first read, and it is much more formal and rigorous than this one. And most of the topics today I have taken from this book. So with this I would end my talk. Thank you for.
So, any questions? If nobody has any questions, yeah, we can thanks people.